Welcome back to Calculus 1. I'm Dr. Jeff Crow, and this is your integration lab. Question 1 is, state the definition of the definite integral. I would like for you to give me the definition in a very particular way. The integral from a to b of f of x dx is the limit as the norm of the nth partition goes to 0 of the sum as k goes to 1, from 1 to n of f of ck delta xk. In this definition, we're allowing the intervals to have varying widths. They're not all the same width. And we're choosing sampling points within each of the resulting intervals in our partition. The norm of the partition is the maximum subinterval size. We're trying to guarantee that the maximum subinterval size tends to 0. As that happens, n has to go to infinity. We have the height of the function times the width of the interval. This gives us areas of approximating rectangles. We add those up, and then we refine the partition, making the divisions smaller and smaller until the largest subdivision tends to 0. When that happens, that is, by definition, the definite integral of our function on the interval from a to b. So this is the definition that I would like for you to produce on the exam. On problem 2, I ask you to estimate the integral from 0 to 2 of x squared dx using Riemann sums with n equals 8 in the first part. Then I ask, what happens if you use n equals 1000 for the second part? And then I ask you to use the fundamental theorem of calculus to find the exact value. The easy part is, of course, to use the fundamental theorem of calculus. Let's use this part first. The fundamental theorem of calculus, what we have denominated the second fundamental theorem of calculus, goes as follows. In order to evaluate a definite integral of some function little f, make sure that you use a lowercase f here. Is it equal to uppercase f of b minus uppercase f at a? We use the notation of uppercase letters to denote antiderivatives. To evaluate the area under the curve from a to b, find an antiderivative, evaluate at the endpoints, and subtract. This gives you the exact area. It's remarkable that anti-differentiation has anything to do with area finding, and yet it is true, established by the fundamental theorem of calculus. Applying the second fundamental theorem, an antiderivative is found by the power rule for antiderivatives. We raise the exponent by 1 and divide by the new exponent. The bar notation implies that we plug the upper number in first and then we subtract. What we get when we plug the lower number in, of course, the second term is 0. 2 cubed is 8. So the answer is 8/3, or exactly 2 2/3. As a decimal representation, that's about 2.666, so on. So we know what the answer is. It's this, the exact value, of course, here. Now let's see what the Riemann sums tell us. Let's recall the formula. The integral from a to b can be estimated using a partition, in this case we're going to have equal width partitions. So the first thing you need to remember is how to calculate delta x. It's the total length of the interval divided by how many times you're going to slice it up. The second thing you need to remember is where these partition points are. X sub k is a plus k times delta x. So for x1, you move 1 delta x over from the left-hand endpoint. When k is 2, you move 2 delta x's over from the left-hand endpoint, and so on. Finally, the Riemann sums are of the form the sum. As k goes from 1 to n, f of xk delta x. In this case, we're using right-hand endpoints, finding heights at right-hand endpoints. Like this. This is not the exact value of the integral. It only gives estimations, better and better estimations, as n gets bigger and bigger. To get the exact value, you need to take the limit as n goes to infinity. So the definite integral is calculated using limits of Riemann sums. This is just a Riemann sum. In this problem, we've been asked to investigate what happens with n equals 8 and also n equals 1000, and we already know the answer is 2 2/3. To evaluate these Riemann sums, I'm going to use a spreadsheet. The x values start at 0. The n value, let's say, is 8 to begin with. We need to calculate a delta x. For the delta x, we take the width of the interval, which is 2 minus 0, divided by how many times we're going to divide this. Now, to get to the next x, we take the old x and we add a delta x, but there's something we have to do here. We have to make this second term an absolute reference. That means we have to put dollar signs around the D. That will always refer to the exact contents of the cell D2. A2 without the dollar signs just refers to the cell above. Let me show you how that works. I'm going to paste this down all the way down here to 10. Notice that the first row is just labels and the second row starts at 0. So to bump 8 units forward, we need to go all the way down to cell 10, row 10 here. And that gets us all the way to the end of the interval. We're going to evaluate the function values on the right-hand endpoints. So that's going to be these things squared. So that's our formula. Notice that these new x's always refer to exactly the cell above. This refers to A4, but this always refers back to the contents of D2. We're squaring the x values to get the y values that are associated with that. Now, the formula said take height times width. The widths are all delta x, and those can all be factored out. So we can just take the sum of these heights and then multiply them by this width. The way to do that might be to hit the AutoSum formula here. That adds up all of those values, but we need to multiply that by the delta x that we factored out. This will give us the value of that Riemann sum. Notice that we're getting 3.1875, which is way off. But we are using only 8 subdivisions in order to estimate this. Let me take these first few columns here. Oops, I'm going to copy those and put them on a new sheet of the spreadsheet. I like to change the zoom factor up to 300% so that you can see what's going on. We're going to change this to n equals 1000.
So if we're going to do 1,000 subdivisions, we should get a whole lot better, a whole lot closer to 2.66 in our answer. We need to paste these formulas all the way down until we go from x equals 0 to x equals 2. We need to go down to row 1002. So to do that, I'm going to press Control G. Control G is the go-to function. I want to go down to A1002. And there I am, right there. My point of insertion, it's highlighted. That's where the cell has been selected. It's very important that you try to understand what I do next. I'm going to grab the scroll bar. I'm going to grab the scroll bar and scroll all the way back up. If I can actually grab this scroll bar, all the way back up to the top. And before I click anything, don't click anything until you do the following thing. Press the Shift key. And then put your point of insertion right over here above cell B3. And then click that. We've highlighted all the cells between A1002 and B3 here. That allows me to paste these formulas down into the selected area by hitting Control and D. Control D is paste down. Let's see if you can see what I've done here. We've now selected everything and pasted these formulas down until we get all the way down to the end here. Let's see if we get a better estimate for the area now. We'll do that by perhaps doing the auto sum again. Auto sum. But we have to multiply by D2 again, remember, which is our delta x. This is significantly better than the answer that we had over here when we had n equals 8. At n equals 8, we're just at 3.1875, which isn't even good in the units digit. At least now it rounds to 2 decimal places. What is the error? 8/3 minus what we have. We're off in the 3rd decimal place by about a 4. And this too is rounded, as you can see if I display more digits. Excel allows us to display a pretty good number of digits, up to a certain limit. So this worked out pretty well. We have 1,000 subdivisions, and we have 2 decimal place, 3 digit. The question that I have next is, what if we use 1,000,000? Let's see, one more, there we go. 1,000,000. We have to paste formulas down again. I'm going to erase all the work that we did to this point so that we can repeat the sequence of steps that we did here. I want to hit Control G. I want to go to A1,000,002. 1,000,002. There's my point of insertion at A1,000,002. I'm going to go all the way back up to the top, Shift, click, Control D. Now, we are performing a large number of calculations. Each of the new entries in the A column requires an addition. Each of the entries in the B column requires a square of the entry in the A column. And this is not the end of what we're going to do either. We're going to go down to the bottom of this and do a column sum, just as we did before. And that's going to require a very large number of additions. So all of this arithmetic, it just takes a bit of time. After all, we are talking about at least 2 million arithmetic operations going on right now. So how long does it take to do 2 million arithmetic operations? Well, in a computer program, you could get it to do these very much quicker than this. At a high-level program like Excel, it takes longer. The higher level the program, the longer the execution. The closer you are to machine code, the quicker the speed of execution. So there we have it. We've done all 2 million of those computations. We're going to come down here to the bottom, and we want to do the sum, the auto sum. And after that, we want to multiply by the contents of cell D2, which is our delta x. So this will do another million additions plus 1 multiplication. So I've hit enter, and there it is. Wow, we are doing better now. Let's see how big the error is. It's this, the difference between this and 8/3. The error is, let's show a few more digits here. Oops. 0.00004, a 4 in the 6th decimal place. That's how far off this estimate is. So as we increase the number of subdivisions and decrease the size of that delta x, the accuracy of this area estimation gets better and better. So at n equals 8, the estimate was really terrible. What is the error? It's the above minus 8/3. We were off by about 0.5. With 1 million subdivisions, we're off by about a 4 in the 6th decimal place. Much, much better. It looks like each time we multiply the number of subdivisions by 10, we divide the error by another 10, making the error smaller and smaller. That's approximately true.
On problem 3, I ask you to evaluate the following integral using the definition. The integral goes from 1 to 3. It's x cubed plus 3x, make that a square on your paper, plus 2x plus 1 dx. On step 1, we need to calculate delta x, which is 2 over n. On step 2, we need to calculate the elements of the partition. That's going to start at 1 and add k times our delta x. On step 3, that's where all of the excitement begins. We'll take the limit as the number of partitions goes to infinity of the sum as k goes from 1 to n. At this point, we have to evaluate our function at each of the xk's and then multiply by our delta x. So that's going to be 1 plus 2k over n cubed plus 3 times 1 plus 2k over n squared plus 2 times 1 plus 2k over n plus 1 all times 2 over n. The 2 over n can be factored out of the sum, but not out of the integral, but not out of the limit. To complete this computation, we're going to have to FOIL everything out. In particular, you need to know how to evaluate the cube of a binomial. For that, you need to remember Pascal's triangle. If I have x plus y to the power n, what do I get? In particular, what are the coefficients of powers of x and y? Pascal's triangle, every new row begins with a 1, and then the next row entry is the sum of the two above. Every row also ends with a 1. We have a 0th row, a 1st row, a 2nd row, a 3rd row, a 4th row, and so on. So for example, if I want to calculate x plus y cubed, I get x cubed, 1x cubed, plus 3x squared y. The powers on the x decrease while the powers on the y increase, plus 3xy squared, and then 1 times y cubed. Pascal's triangle makes it easy to raise any binomial to any power you wish. Each line on our calculation begins with equals, and the thing immediately after the equals will be the limit as n goes to infinity, at least until we actually evaluate the limit. I'm going to factor the 2 over n out. And now we need to cube out this first binomial. So that's going to be 1 cubed, which is 1, plus 3 times 1 squared times 2k over n, plus 3, 1, 3, 3, and then 1. 3 times 1 times 2k over n squared plus 2k over n cubed, 1 times 2k over n cubed. Now we need to multiply out this perfect square. That's 1 plus 2 times 2k over n plus 2k over n quantity squared. Now we have this 2 plus 4k over n plus 1. The next line begins with equals, and don't be dropping my limits. Don't be cheap with me. Don't lose notation. Try to make true statements. We have this 2 over n. Now in our sum, we have this 1, we have a 3, that's 4, plus 2 is 6, plus 1 is 7. We're adding 7. Here we have a 6k over n plus another 12k over n. 6 and 12 is 18, plus 4 is 22. So that was 6, and 6 times 2 is 12, makes 18, plus 4. Now how about the k squared terms? We've taken care of these. Now the k squared terms. This 2 gets squared, so that's going to be 4 times 3, which is 12. This 2 gets squared, and so that's going to be 4 times 3. It's another 12. And so 24 k squared over n squared. That takes care of these terms. That leaves only this last term, which has a 2 cubed. That's going to be plus 8k cubed over n cubed. Remember that if you have the sum as k goes from 1 to n of some constant, you get a constant times n. For each of these indices k, you're just adding c, so it's c plus c plus c, however many times there are for that index in this case, in different values for the index. We're going to have the limit as n goes to infinity of 2 over n, 7n. You also need to remember the 3 formulas. The sum as k goes from 1 to n of k is n times n plus 1 over 2. If we're looking at the sum as k goes from 1 to n of k squared, that's n times n plus 1 times 2n plus 1 over 6. And the sum as k goes from 1 to n of k cubed is the quantity, n times n plus 1 over 2, quantity squared. On this term, we can break the sum into several pieces. The 22 over n comes out, and we're just adding these k's. When we add up the k's, we'll have n times n plus 1 over 2. On the next term, we have 24 over n squared that factors out. The sum of the k squareds is n times n plus 1 times 2n plus 1 over 6. And on the last term, we have 8 over n cubed times the quantity n times n plus 1 over 2, quantity squared. We can distribute this n and cancel off one factor of n from each of the resulting terms. So canceling this with one factor of n from each term, I'll just make this exponent 4 on the last term and do my cancellations later. We're now ready to calculate the limit. We'll have 2 times the quantity, 7. There are no more n's on this first term. On the second term, n plus 1 over n has a limit value of 1 as n goes to infinity. Remember, you take the ratio of the leading coefficients. That leaves 22 divided by 2, and that's just 11. On the next term, we have n plus 1, 2n plus 1 over n squared. 6 goes into 24 4 times. We'll have 2n squared as the leading coefficient over n squared. These will tend to 2 times the 4 gives us 8. And on the last term, we have a 4 after we square, which goes into the 8, leaving a 2. N squared will cancel with 2 of the n's. N plus 1 quantity squared will match the remaining n squared in the denominator. As n goes to infinity, the leading coefficients are both 1, so the n's all cancel out, and we just end up with 2. So what does this add up to? 11 and 7 makes 18, and 2 makes 20, with 28 times 2. That's 40 and 16, which is 56. This is what we get using the definition to evaluate the given definite integral. Let's check this answer using the fundamental theorem of calculus. The original problem was the integral from 1 to 3 of x cubed plus 3x squared plus 2x plus 1. By the second fundamental theorem of calculus, this will be x to the 4th over 4 plus x cubed plus x squared plus x evaluated from 1 to 3. Plugging in the 3 to the power 4 is 9 squared, which is 81. 3 cubed is 27. 3 squared is 9, and then 3. From this, we'll subtract what we get when we plug in 1. 1 plus 1 plus 1 is 3 that we're subtracting. Those all cancel. 81 fourths minus 1 fourth is 80 fourths, which is 20. 20 and 27 is 47 plus 9 is 56, or a big check. On problem 3a, I ask you to integrate 1 over 1 plus x squared dx. I want you to know that this is the 1. This is the one that I asked you to remember. This is the arctangent of x plus c. That's completely different from part B. And you know I'm going to give you both of these on the exam. That's because I want you to pay meticulous attention to the details. The x in the numerator here makes all the difference. This is almost in the form f prime over f. The derivative of the denominator is 2x. If only I had a 2 in front of that x. But I can make a 2 in front of that x if I put a 1/2 out front. Now I do have an integral of the form f prime over f. So the answer is 1/2 the natural log of the absolute value of 1 plus x squared plus c. In this particular case, the absolute values are superfluous because 1 plus x squared is already positive. Part C is related. We have x plus 1 over x squared plus 1 dx. I want you to be able to see in your mind's eye that you can rewrite this very quickly as two integrals. The first integral looks like the second one that we did, and the second integral looks like the first one that we did. So you get 1/2 ln absolute value of x squared plus 1 plus the arctangent of x plus an arbitrary constant of integration. On part D, we're integrating 1 over the square root of 1 minus x squared. I want you to know that this is the other one that I asked you to remember. And that's arcsine of x plus c. On part E, we're integrating 2x plus 2 over x squared plus 2x plus 3 dx. The derivative of the denominator is 2x plus 2, which happens to be the numerator. That means this is of the form f prime of x over f of x, and we know all of those are log absolute value of f of x plus c. So the answer is immediately log absolute value of x squared plus 2x plus 3 plus an arbitrary constant of integration. On part F, we're integrating e to the x over e to the x plus 2, again in the form f prime over f. So the answer is automatically log absolute value of e to the x plus 2 plus c. On part G, we have an indefinite integral of the sine of 7x dx. We know an antiderivative of sine of x is negative cosine. But because of the 7 here, we divide by 7, and of course add plus c. You can see that if you were to take the derivative of this, the derivative of cosine is negative sine, so you cancel out the negative. But by the chain rule, you have to multiply by the 7, and that would cancel out the 7 here. Anytime you're integrating the sine of omega x dx, you will get negative 1 over omega cosine omega x plus c. On part 8, we're integrating from 0 to pi over 2 cosine of 2x dx. Now, it is possible to use the fundamental theorem of calculus to evaluate this. But I want you to remember something else. If you have cosine of omega x, the period is 2 pi divided by omega. The period in this case is 2 pi divided by 2, or pi, which means for this particular cosine function, which always starts up, makes it dip down like this, we complete one cycle in pi units, which means that if we're integrating pi over 2, we have to have half a positive bump and half a negative bump for a grand total of nothing. No further computation required. Some of you might be disbelieving about how easy it was to arrive at a value of 0 for this definite integral. If you would like, go ahead and use the fundamental theorem of calculus to evaluate it on your own. However, whenever you integrate cosine over half a period, you get nothing. For sine, you have to integrate over the whole period so that you get a positive bump and a negative bump to cancel out. If you integrate cosine over a whole period, you will, of course, get 0 in the first half and 0 in the second half. 2 times 0 is still 0. But the principle you need to remember is, if you integrate cosine over half a period, you got nothing. On part I, we're integrating from 1 to 5 of x times the square root of 2x squared plus 4 dx. It looks like we have the derivative of something more or less lying around. So this is a u substitution. U is 2x squared plus 4, so that du is 4x dx. We don't have the 4, so we're going to divide it off. We're going to transform the limits. If x is 1, u is 6. And if x is 5, 5 squared is 25 times 2 is 50, plus 4, we get 54. The x dx goes away to become a 1/4 du, and then we'll have u to the 1/2. This is 1/4 u to the 3/2 times 2/3, evaluated from 6 to 54. Notice we have a coefficient now of 1/6. Whenever we take a number and raise it to the 3/2 power, that's a to the 1 plus a half, or just a root a. 54 is divisible by 9, but first let's just write this as 54 root 54 minus what we get when we plug in 6, which is 6 root 6. Let me write that over. That's 1/6 times 54 times 3 root 6 minus 6 root 6. Now, we can divide this 6 through, how many times does 6 go into 54? 9 times, so we get 27 root 6 minus 1 root 6. That's 26 root 6. On part J, we're integrating from -5 to 5, x square root of 2x squared plus 4 dx. This looks a lot like the last problem, but it has a much simpler solution. The answer is 0 immediately, and that's because the integrand is odd. What makes it odd? Perhaps it does inappropriate things in social settings? No. A function's odd if f of negative x equals negative f of x, and all such functions have this kind of symmetry. Whatever happens at x, the opposite happens at negative x. In this case, the function is x times 2x squared plus 4 under a radical, so that f of negative x gets a negative propagated here, but the negative on the square goes away. Whenever you integrate an odd function from negative a to a, you get 0. So just by looking at this, you can see that the square takes a negative out here, and you get one negative pulling out front. The integrand is odd. You're going from negative a to a. You have to get 0. On part K, we're integrating secant of x dx. those of you who remember this will know that this is the log of the absolute value of secant of x plus tangent of x plus c. You know it or you don't. This was the garbage can calculation that I asked you to remember from earlier. Please take note of it. On part L, we're integrating from 0 to pi cosine squared of x dx. Cosine squared always requires a half angle identity. I ask that you remember the half angle identity. Now the period of cosine 2x. If we take 2 pi and divide by 2, we get a period of pi. We're integrating over the whole period, which means this term contributes no area at all. In what's left, we're integrating the constant 1/2 on an interval of length pi. If you integrate a constant, k, on an interval of length b minus a, the area is k times b minus a, height times width. In this case, the area will be pi over 2, pi times a half. On part M, we're integrating from -2 to 2 the square root of 4 minus x squared dx. This may look like a problem that we did earlier, but it's completely different. The integrand here is not odd, it is even. What is more, if I write y equals the square root of 4 minus x squared and then square both sides, and then rearrange this, you can see right away that we're dealing with a circle of radius 2. But because we're dealing with the principal square root, we're only dealing with the upper half semicircle. So the area is half the area of this disk, which is pi times the radius squared. The answer is 2 pi. On the next problem, we're integrating from 0 to pi sine squared x dx. This too requires a half angle identity. We write the integral from 0 to pi of 1/2 1 minus cosine 2x dx. What is the period? 2 pi divided by 2 is pi. We're integrating over a whole period. The second term contributes nothing. And the answer is height times width, pi over 2. On problem O, we're integrating 1 over x dx. You know it or you don't. Log absolute value of x plus c. Don't be cheap with me. Give me my absolute value. On the next problem, part P, it's 1 over x ln of x dx. It looks like we have the derivative of something lying around. If u is the thing that has its derivative lying around, then du is 1 over x dx. I can take this x here and put it on this dx as a 1 over x dx. The integral transforms as 1 over u du. This part goes away to become the du, and then we're left with this 1 over u. We get log absolute value of u plus c, but then u is natural log of x. So we get the log of the absolute value of the log of x plus c. And now we're at the last problem. The integral of the tangent of 2x dx. Tangent always needs to be broken up into sine over cosine. And just to be careful, let's do the u sub. U is going to be cosine of 2x, so that du is minus 2 sine of 2x dx. We have to use the chain rule, and that gives us the factor of 2. The derivative of cosine is negative sine. We don't have the negative 2, so I'm going to divide it off. So I have negative 1/2 times the integral of 1 over u du. The numerator here goes away to become the negative 1/2 du, and then the cosine is replaced by u. We get negative 1/2 ln absolute value of u plus c, and then substituting back, negative 1/2 ln absolute value of cosine of 2x plus c.